a little. Can we make anything? Can we make it louder? Okay. Okay, so I'm going to start passing around an evaluation. All you have to do is write your UCF ID, only your numbers, and then you have to bubble in the number provided, which is that 65, so at the top a 6 and then at the bottom a 5. It's just to see how the session went, how study union is going, and I'll be collecting them at the end. So you can either bring them to me at the end or place them on the first table. And we'll get started in a little bit. Study union evaluation. Okay. Wait, you have more people?
Is this like the same evaluation you did last time?
This is different. Yeah. Just pass them. If you didn't get one, it's fine. Considering I'm not working anymore, but that would be good. Thank you. That's nice. Yeah, I'm just going to say that. I'm trying to figure out how to put on the mic. Okay, so for those of you who don't know where the review is, if you go to ucfstudyunion.wordpress.com, you're going to find it under physics, and it's the very first session that it says. So you can either pull it up on your computer, or if you need to, we have like 30 seconds for you to go upstairs and go print it, or you can get someone to print it, yeah. ucfstudyunion.wordpress.com, if I'm not mistaken. And if you don't get an evaluation, that's fine. I only have a handful of those. Just make sure that if you do get it, you fill it out, and then you bring it back to me. Are we good? Okay, so it's 2:30. We're going to get started. Is the sound better now? Yes? Okay. So we're going to get started. The review that we'll be going over is, again, the one I just told you about, the one I posted on the WordPress side. This review is being recorded. So if for some reason you didn't get to understand something and you need to go back to it, you can find us on YouTube. It's going to be Physical Science with Maria, and it's going to be under UCF Starks channel. So if you need it, that being said, it's being recorded. So if you have to ask a question, just make sure that your language is appropriate and all that. This review is a bit short. My idea was to have enough time at the end for you guys to ask questions. However, if throughout we go over a problem or a concept that you're still unsure about, please don't hesitate to raise your hand. That's what we're here for. And then you'll see that at the end, if you do have the review, I included a new part that maybe we haven't done before, and that is a formula sheet with a bunch of names and formulas. That is just kind of to guide you. I left blank spaces at the end just in case I didn't write all of them, and you could add more. If we get time, we'll fill that out, but I don't think that's as important as talking about one thing that you guys have been mentioning throughout the entire semester, and it's talking about the scientists and what they came up with, what they discovered. So we'll be also going over that after we go over all the questions. There are not as many very in detail problems. However, if at the end we have time and you guys want to do a specific one, maybe thermal equilibrium or anything like that, just ask and we will go over those. Quick reminder, the session number is 65, the number that you have to put in at the top of those of you who have evaluations. And as we go, if we do use formulas, I'll be referring back to the formula sheet and kind of trying to fill it out as we go. Just to kind of like tell you what this is for, you'll write the formula. So we have the name, then you will write the formula. The unit is, for example, what do we measure velocity in? And then the symbols, it would be what is delta V. So you're writing the name of what is delta V and all that. Questions so far? Everybody good? Great. Okay, so again, we're gonna get started. As you guys know, I forget about the projector, so let me know if you can't see what I'm talking about or what I'm writing as we go. The first question, and all of you have a phone or a computer, so all of you should be calculating everything that we do. So please check, because sometimes we will have mistakes, and I don't want to be writing something that's wrong, and then you go in and say, how did she get that? So the first question is, what is the weight of a 40-kilogram person? And this is going back way to the beginning of the semester. So how do we calculate weight? Great, thank you. So it's W times mg, and again, I'm pretty sure, yeah. And that is a formula we have right here too, if I can find it, okay. And what do we measure weight in? What's the unit? What? What do we have? So we have mass, which is, what's the unit of mass? Kilograms, great. What about gravity? What's the unit of gravity? Meters per second what? Great. So meters per second squared. So when we're multiplying, you would do kilograms times meters per second. And meters per second squared, sorry. Does anyone know what unit that is? Yes. Thank you, Kiana. So yeah, that's a Newton. Whenever you're taking the test and you don't know what the unit of something is, if you do know the formula, you can do this. This is why it's important to know what do we measure mass in, what do we measure gravity in, so that you can then combine it and figure out, because you'll see that sometimes the number will be right, but it will have different units. So that's also important to know. And weight, it's not like what we thought before, like you go in a scale and you measure your weight. Weight is a force. So it's the force of what? The force of attraction, so how Earth is attracting different objects. So we'll do W is mass times gravity. So we know that mass is 40 kilograms. And what is gravity? Great. And what's the unit of gravity? Meters per second squared, thank you. So who can multiply that? Perfect, thank you. Can anyone check to see if that's the number? 392? Great. We're going to keep going. So for number 2, all of the following are correct formulas for deltas, except which one? Great. Why do you think it's B? Exactly. So let me see if this works better. Okay, yeah. So B is the one that doesn't match, because when we do deltas, it's always later minus previous. So 2 minus 1 is never the first time versus minus the second. It's always the second minus the first. The other ones are not T2 minus T1 or V2 minus V1, but they are also different formulas that we have used throughout the semester. So if we went back to our formula sheet, what do you guys think this one comes, where does this one come from actually? What? It's the acceleration one. So it's solved for delta V, but it's actually, if you go to it, it's A equals delta V over delta T. So that's another formula we talked about at the beginning of the semester. So A equals delta V over delta T. What do we measure acceleration in? What's the unit? What's the unit for acceleration? Meters per second what? Thank you. So if you think about it, gravity is a type of acceleration, so they have the same unit. So it's meters per second squared. Now, what is the unit for velocity? What's the unit for velocity? Yes, great. So meters per second. Because acceleration is the rate at which the velocity changes over time. So when you think about it, it's kind of like velocity is the small, velocity is the small thing, and then it's how much you're going in a specific time versus acceleration is how much you're changing over a period of time. So that's why the acceleration has the squared over the second part. What are the two components of velocity? Speed and, I heard it, time not. Yes, so the two components of velocity, are speed and direction. So I think we're gonna cover that in a second. Yeah, in a little bit, I think I have a question about that, but just keep that in mind, that velocity is not only the number, it also has to do with the direction of something. And then this formula, delta x equals v times delta t. Where's that coming from? So think about the graphs that we did. Is that a distance rectangle or a distance triangle? What? Think about when you're talking about area. When you find the area of a rectangle, what do? Base times height, right? So this is actually distance rectangle. So right here. And who knows what delta x is? Great. And that is the same as? So we measure it in meters. So is it velocity, distance, acceleration? If we measure it in meters? Yeah, so it's distance. V we said was velocity, and delta t we said was time. Oops, my bad. Everyone good so far? Okay. So this is from the first exam. Wait. We'll go back to that one. So this is from the first exam, actually. So we have this graph of time over velocity. So how would you guys define the motion between 0 seconds and 2 seconds? Is the object slowing down? Is it speeding up? Is it at rest? Or is it moving at constant velocity? Great. So yeah, it is moving at constant velocity. If you see it, the line is straight. So that does not mean that it's not moving. It's just that at 1 second, it was moving at 1 meter per second, and at 2 seconds, it was still moving at 1 meter per second. And then what happens between T2 and T4? Is it slowing up, going backwards, gaining speed at a constant rate, or is it at rest? It's speeding up at a constant rate. So the reason why we say it's speeding up at constant rate is because that line is straight. If it had different inclinations throughout, then it wouldn't be speeding up at a constant rate. The acceleration will be changing. And now I'm going to leave this here and then go to the questions up here. So by finding the area, what are you finding? Are you finding the distance, the acceleration, or the force, or nothing? Great. So yeah, it's actually the distance. So this is where all of our formulas about distance triangle, distance rectangle, the drop distance formula, this is where they are all coming from. If you have acceleration, this is what your graph is going to look like. So you're going to have the 1/2 in your distance formula. If there is no acceleration, so the graph looks like this, then you're just going to be using the one we talked about before, where the distance rectangle of delta x equals v times delta t, because again, you don't have any acceleration. Now, how can you calculate the acceleration of the object? Do you calculate the area, the slope, or you can't calculate it? You have mass. What's the unit of mass? Kilograms, great. And what's the unit of velocity? Great, meters per second. So that's it. Whenever you don't know the unit of something and you do have the formula, just write down everything, multiply, cross out whatever you can, and that's it. Okay, so this one. What is latent heat of fusion? Is it the amount of energy needed to break bonds in liquid state, in solid state, energy needed to increase the temperature of the object, or none of the above? So think about, when do we use latent heat of fusion? In what type of problems? The heat melt heat problems. Do we use that part when we're heating it or when we're melting it? When we're melting an object. So we know it has nothing to do with the increase in the temperature, so it has something to do with the state. It's just going from one state to the other. And when we're doing it, from which state to what state are we going? We're going from solid to liquid. So in that point, the bonds in the solid state are stronger, so we need to break them in order to go from solid to liquid. So it is breaking the bonds in the solid state. What is the latent heat of fusion for water? 80. So when we go to the heat melt heat problems, you would heat it with the Q equals mc delta T, which is, okay, I have it. If you go to the back of the formula sheet, we have general heating up formula and general melting formula. Those are just the names I gave them. I don't think they really have a proper name. We were not given one. So the heating up would be Q equals mc delta T. M is what? Mass. What about C? Great. Specific heat. So this is actually a great point. Someone said calories. Calories is actually Q. So that's the amount of energy required. Those are the calories. C is just a specific heat. Now, what is the specific heat of water? 1. And ice? 0.5. To remember which one is less, just think about the fact that ice is easier to heat up, so the number is smaller. And then delta T is, in this case, we don't talk about T in terms of time, but T in terms of temperature. So it's a change in temperature. And what's the melting formula? When we go from one state to the other, what do we do? The other Q formula. Yeah, so MLF. So mass times latent heat of fusion. And again, QE is the calorie, so Q is energy. Any questions so far? Okay. So now we're going into waves. This is not really organized in the order that we went over things, but anyway. Waves transport blink and blink across space-time. Is the first one, do they transport energy or force? energy. So we know it's energy. So it's not C and it's not D. And is it motion or momentum? Yeah, so it's momentum. So think about when we were talking about waves, we talked about potential energy, kinetic energy. So kinetic energy is the energy of what? Kinetic energy is the energy of motion. And then, so the waves are moving, so they have that. And then momentum, if you look at the formula, is n times v. Waves have a mass, and they also have a velocity, so they are carrying momentum as well. So sometimes if you don't know something, all the formulas are derived from the concepts that we've gone over. So if you try to add formulas and you're like, okay, this just doesn't match up, then maybe that doesn't work for that. What type of force is the spring force? Great. So restoring just means that the object's going to move, but it's always going to go back to what state? To equilibrium. So it's going to go to max extension, go back to equilibrium, but the force is going to pull it back towards compression, and then it's going to eventually go back to equilibrium. Wait, and we do have, what is the spring potential energy? What? Does everyone agree with that? You guys have that formula? Okay. And do we have the spring force one here? Okay, we don't have that one. But the spring force, does anyone know that one? So we're talking about spring, so we have only k and x. So that would be negative kx. And that is spring force. What is k though? And what is x? K is the constant, so the spring constant. Now, for the spring constant, unlike gravity, which is also a constant, for the spring, the constant changes depending on the spring. Just like specific heat is specific of water and of ice, the same thing with this one. What about x? Distance from where? Great. So you can either call it displacement or distance from equilibrium, whatever you think is easier to remember. Okay. And I'm not going to write it down here, but those are the same. We're talking about down here in the spring force, we're talking about the same thing. So K, spring constant, and then X is displacement. Now, in general, the problems with these two formulas are very straightforward. They just tell you spring, and you have to know the two formulas, and they'll ask you to either calculate the spring potential energy, or tell you, and they'll give you the constant and the displacement, or they'll give you the displacement, and you'll have to find, no, they'll give you the spring potential energy, and then you'll have to find the displacement. So it's dependent on the problem, but they are very straightforward in how to use the formulas. Now, which of the following is not a mode of heat transport? Is it conduction, convection, convulsion, or radiation? Convulsion. So, when we talk about conduction, we're talking about the physical contact, of something hot with something cold. So, as we've been talking about the heat in all the heat problems, when two things are, when you have something that's hot and one thing is cold, they're going to try to find that thermal equilibrium. So the one that's hot is going to it's going to lower its temperature, and the one that is cold is going to raise its temperature so that they find a balance. And then when we talk about convection, that's when conduction is not so rapid, and then you get bulk motion. So it's usually when you have when we talked about that person with I'm pretty sure he used that example of the guy with the fire. So it's when you have that fireball racing upward, and then also when you have boiling water, thunderstorms, hurricanes, or turbulence. Also, so when you think about it, if something is not able to conduct heat rapidly, then it has convection. And then radiation, we talk about electromagnetic radiation. So if for some reason they ask you about what does an astronaut is protecting, what is an astronaut protecting himself from? When he uses the helmet, he's protecting from radiation, because kinetic energy is carried by photons of light, and then they emit this radiation, and then the material that finds the radiation just heats up. So these are the three ways to transport heat. I know I went, any questions? Great. Okay, so this is, I don't know why I wrote it like this, it's kind of weirdly written, but the question is converting 6 grams of water from 303 Kelvin into a block of ice at melting point requires the loss of this many calories. So what I'm asking you is to go from 303 to the melting point, which is what? 273, great. So we have to go from 303, we have to go down to 273, and I'm telling you, I had water, but I want it to be ice at that temperature. So if we were to, it's kind of weirdly written, but if you were to name this problem like we name heat, melt, heat, what would this problem be like? What? And then what else? Solidify. Yeah, you got the idea. So yeah, it's heat melt, but in this case, you're going from 303 down, so it would be cooling the object, getting to 273, and then at 273, just going from water to ice. So you have to use the two formulas that we just talked about. So Q equals mc delta T, and Q equals m times latent heat, but we're not doing it to a point where you change again the temperature. So let's work it out together. So again, we just write everything that we have. We have the mass, which is, and this is number 15. The mass, which is 6 grams. This is something very important here. In this type of problems, the mass is not kilograms. We're going for a mass in grams. Then we have the initial temperature, which is 303. And then we know it's going to go all the way to 273. What else do we know? We know we're talking about H2O and we're talking about ice and water. So what is the specific heat of ice? 0.5. And what about water? 1. And the unit is calories per gram Kelvin. And then what else do we know? We know the latent heat of fusion, which is calories over grams. And now, so we have to do two parts. We have to go, the first one is going from 303 Kelvin to 273. So in this case, delta T, we said that it's final minus initial. So we're going to do final, which is 273 Kelvin minus 303 Kelvin. What is that? Negative what? 30 Kelvin. Why is it negative? Yes. So in this case, so far we've been doing heat melt heat, so we've been going up. But in this case, we're cooling down the object, so it has to be negative. First, because we have final minus initial, and because if we're going down, are we gaining or losing heat energy? We're losing heat energy because we're cooling down. So when we talk about thermal equilibrium, the same thing happens. One object is losing those calories, and the other object is absorbing them. So we have delta T. So now we can use our formula of Q equals MC delta T. Now, what C are we going to use? 0.5 or 1? 1, great. So we're not going to use the ice one because we are above 273, so what we have is water. So if you have water, you use the water one. So we know the mass is 6, the specific heat is 1, and then the delta T is negative 30. And I didn't add everything else, but that is 180, right? And it's negative 180 again because it's losing it. And now the second part is not the part where we keep on going down in temperature. It's just the part where we go from one state to the other. So from liquid to solid. And that is what we use the Q equals MLF. Q1. So Q2 equals the mass times the latent heat of fusion, which is 80 calories per gram. Grams cancel out. So it's 480. Percentage. So for the total Q, we need so for total Q, you just add all the Q's. Oh, sorry. So you add the Q's. So that's a great question. In this case, because you're going down, the bottom one is also calories you are. That was funny. Okay, so in this case, you are losing the calories all the way through. So even this ones are calories you are losing. Does that make sense? So because you're going from the solid state, you're going from the liquid state into the solid, those are all calories you lose. So you add them together. And then you got it 60. Either way, we haven't done problems going down in temperature. I just did it so that we could kind of like better understand everything. So far, we've done just problems in which your temperature rises. Yes? So in this case, we're talking all about the calories you're losing. So I know at the top it's negative because you did the delta T, but those are all calories you are losing. So going from when you're going down, those are calories you're losing. Because you're going from a higher temperature to a lower temperature. So because you're changing those, you are losing the heat energy because calories is heat energy. So if you think about it, you were hot, so you had a bunch of heat energy. Now you're going cooler, so you're losing that heat energy. You're losing those calories. So again, it's negative at the top because we're using the delta T, but the second one should also, the second part is also calories you're losing. So you can either have both of them negative or have both of them positive. The thing is, the way the problem is worded is asking you for the calories you lost. So you just have, in this case, you don't have to indicate that it's negative because it's already telling you that you lost them. So you would just do 660. I know it's kind of confusing right now, but I wouldn't really worry about that because so far we've only done problems where your temperature rises. So those, in that case, your numbers will always be positive. The reason why I did it again is so we could cover more things and I wouldn't forget. Okay, so for the next one, we kind of talked about it, but what happens to a group of objects that interact? A, conservation of momentum. B, the objects are going to move with a new velocity. C, you can use the momentum formula to find the new velocity of the objects. D, there are two momentum states, none of the above or all of the above. So we talked about the first one. Is the first one true? Yeah, so we know that one's true. Think about, whenever you don't know about what they are talking, think about an example. What is an example of conservation of groups of objects that interact? The boxcar problem and the blobs. So in both of them, did the objects move with a new velocity? Yeah, so that was one of the things we calculated. So we already know we have two that are right, so it's all of the above. So we have conservation of momentum. We said it was pi equals pf. The objects are going to move with a new velocity, and the way to find it, because that's basically what we do in the boxcar problem, and when you have that blob problem, is you use the p equals mv, and then you use that formula to find the new velocity. And there are two momentum states, again, because you have conservation of momentums. We have things that are interacting, so before they interact, there's a momentum state that you have to calculate, and after they interact, you also have some momentum that stays the same. Questions about that problem? And I'm going to write down the steps for those types of problems because I don't think we have one, but I'm just going to write them anyway. So if you were to solve one of that, would be you can also call them collisions. So they might tell you if a group of objects collide, that would also be a way to know this is the type of problems we're talking about. So they'll usually give you, they'll tell you this object is moving, and these other ones are not moving, or this object is also moving. So the first thing you have to do is calculate the initial momentum. So your initial momentum would be calculating it by doing P. Initial would be P1 times, P1 is the PI. So it would be the momentum of the first object plus the momentum of the second object plus the third one, and so on. So however many objects you have, you calculate it. And that's the same as mass of the object 1 times velocity of the object 2, v2, v3. Now, when we've been doing this problem so far, we've had two instances. So when we had the boxcar, the object 2, 3, and 4 were not moving. So if they're not moving, they have 0 velocity, so when you plug it in into the formula, you get 0 for that part. So you can either, if you remember that, then you can just skip that part and just calculate for the one that's moving. Now, if you have two objects that are moving, if both of them are moving, you have to calculate the velocity of both of them. And then once you have that, the second part is conservation of momentum. And you can also skip this part once you understand it. But basically, it's saying that PI is the same as final. And now for the third part, you want to calculate the new mass. So if you have 4 objects, you just add all the masses. If you have 2 objects, you just add all the masses. They might give you the mass. I remember when we did the blob one, he gave you the mass, so you're good if you have it. But if not, just calculate it. And then for the final part, you just use the, you just calculate. He always asks for the new velocity. So you would use, again, the P formula, the momentum formula. This time you would do the final is the same as the mass of the new object, and the velocity, the new velocity, or the final velocity, however you want to call it. And you will be using the same momentum that you found here. Questions? This is, again, something you can do with any of the problems, with the thermal equilibrium, with the ones we did before. You can just list, if you've been struggling to remember how to do it, just list all the steps that you're taking, and it might be easier, and you can create a flashcard and study that one. How do I don't. Then great question. So let's go back to this one. That is a great question. So to calculate the new velocity, this is what you're going to do. So we have to leave v nu on its own. So we would do, we have to get rid of this mass. So because it's multiplying, we divide this side by that, and then we divide this side by that, which means that this mass cancels this one. So we are left with the new velocity is the same as PF over. Again, if you struggle with solving for formulas, memorize them. If it's easier, if you want to learn how to solve formulas, how to solve equations, that will be amazing. Some of you only have until tomorrow, so it's your choice. There we go. Okay. We are getting into one of the concepts that you guys asked me to go over. So which of the following is a characteristic of uniform circular motion? Is there acceleration in uniform circular motion? Yes. Is speed constant? Yes or no? Yes. Now, how is it that you have acceleration but the speed is constant? What? Great. So the direction is changing, which I'm pretty sure. Okay, I don't have it. Okay, I don't have it. So the direction is not changing. So your number, if like think about it. So when you talk about uniform circular motion, you can think about if you're driving and you're taking a turn for a moment, you're going in uniform circular motion. Now, the motion in itself, unless you hit the gas pedal, is not going to make you accelerate. You're going to maintain, it's not going to make your speed change. So that number, that whether you're going 25 miles per hour or 20 meters per second, that number is going to stay the same. What's going to change is your direction, because you're making a turn. So obviously, you have to be changing your direction. And we said before that velocity was not only speed, but was also direction. So both of them are components of velocity. So this one, your velocity changes, and therefore acceleration is a change in velocity, taking into account the vector. So even though your number stays the same, your vector, your direction vector is changing, so you are accelerating even though the number stays the same. The velocity vector is tangent to the path. So if you were to draw it out, so let's say this is your turn, the velocity is never going to touch the path, it's always going to go like that. So if you're right here, this would be your velocity vector. And then the velocity, the vector of the net force, it's towards the center. So this would be your net force. And there is a circle here that it's called what? Which is, that doesn't look like a circle, but anyway. What is that called? Radius of curvature, yeah. So that's the radius of curvature, and every time you have a uniform circular motion, you have a radius of curvature. It's just telling you how tight is your turn. Now, within the same, so it's all of the above. So what is centripetal acceleration? Is it the acceleration in uniform circular motion? Is it an acceleration that creates a vector pointing towards the center of the radius of curvature? An acceleration in which the speed doesn't change, or a result of the centripetal force, or all of the above? Great. So yeah, we talked about all of them. When we talk about that acceleration when we're in uniform circular motion, it's called centripetal acceleration. You're turning, so you have that acceleration which doesn't change the speed, but changes the velocity, and there is acceleration, and it's a result of centripetal force. So very easy, when we're talking about centripetal force, you have centripetal acceleration. And that is the force, again, that if you're driving and you're taking a curve, you know how after once you're done with the curve, you have to twist your steering wheel so that you don't keep going? That's the force that's making you keep going, keep following that radius of curvature. And now that we're talking about centripetal force, what's it dependent on? Is it the speed, radius of curvature, mass, or gravity, or a combination of those? So we're talking about force. What is the equation, the formula for force? What? Mass times acceleration. So F equals ma. So we know there is some, think about it. When you're driving, when do you experience more force? When you are going faster or slower? Faster. So we know speed has something to do with it. What about if you have a tight turn? Is it going to be the same or different from a turn that's not as tight? It's going to depend on the turn, so in the radius of curvature. So it's A and B. It depends on, is your turn very tight so you have more force that's still pulling you towards the turn? So think about it, if you're in a highway, like not I-4, but any other normal highway, and you'll see that when you have a higher speed limit, the curves are not as tight. You'll barely feel it because we don't want that force to be as strong. You need it to be kind of like smooth so that you don't have to turn your steering wheel as much. And again, it's because it's dependent on your speed, how fast you're going, and that radius of curvature. And this is, work is something I don't think we talked about too much, but bless you. Well, we did talk about it. So if you lift a 4.5 kilogram keg from floor level to 2.5 meters above the floor, how many joules of work are required for you to perform? Does anyone know the formula for work? Yes? What? Great, so that's one of them. You can either use work equals change in kinetic energy, and then there's another one. And that one is the one that we're going to use for this one. Because that one you'll have to calculate more things. That one is a good one. So we have work equals change in kinetic energy, and then work also is force times distance. So either one works, and the unit of work is what? What do we measure kinetic energy in? Joules. Great. So if it's change in kinetic energy, it stays being joules. So joules. So if you're lifting, what type of force is also acting? What? Weight force. What? Great. So we're talking about the force that we're going to use is going to be the weight force, sorry. And then the distance is going to be that 2.5. So we're going to use, for number 20, for work, you need F times Z. Again, you always write everything that you have. So you have the mass, which is 4.5 kilograms. And then you have the distance, which is 2.5. And what else do we know? We also know gravity, which is 9.8 meters per second squared. And then this formula, because the force we're going to use, weight force, would look W equals mass times gravity times distance. And then that would give you, the mass is 4.5, the gravity is 9.8, and the distance is 2.5. So, can anyone calculate that? Did you guys get that? 110.25? Great. So in my case, I don't really care about how many decimal points you put up there. When you're taking the test, Dr. V is very specific about that. So make sure that whenever you plug in a number, whether it is, usually with the iClicker at the end, that's when you'll have to make sure that you're plugging in the right number. Just make sure that you check that before you just plug it in. Yes? Great question. So when you're lifting something, the force that's acting against you is the weight force. Because it's a force that is pulling the object down. So that's what the force that you kind of like went against, because you were lifting it, that's the force you had to kind of like work against, if that makes sense. So, yeah. So all of the above, all of the following are true of centripetal. I know I have said this way too many times, so you should all know that one. But all of the following are true of centripetal acceleration, except which one? What? Is it that it doesn't speed up the object, it does not slow it down, it speeds it up or slows down the object, or it changes direction of the object? What's the answer? If you go 2 questions back, 2 questions, we talked about it in question 18 and 17. So the only thing that centripetal acceleration doesn't do is speed up or slow down the object. Again, the speed stays the same. The velocity is what changes. And the direction also changes. Because, so the speed doesn't change, but because the direction changes, then the velocity changes. Okay. Where is this? In uniform circular motion, velocity is blank. Is it parallel, tangent, perpendicular, or tangent to the path, to the circle path? And blank to the radius. Is it tangent, parallel, or perpendicular? So I'm going to turn it. And the answer is tangent and perpendicular. So I'm going to draw it on this side and then write it down here. And then perpendicular. So we just draw it. You have a turn. Let's pretend that's your road that you're going on, and then you have a turn. Again, this is your radius of curvature. So this is your radius. And then you're going here, and this is the direction of your velocity. So it's tangent to the path, and it's perpendicular to the radius. So this is your radius. This is your velocity vector. All the questions that I'm putting up here, or that I came up with, were things that I remember from tests that I took and that I've seen in different homework assignments throughout the semesters. So for an object in uniform circular motion, the object's blank causes the object's path to point inward. So is it centripetal acceleration, net force, inertia, or velocity? What? So think again. You're on your car, you're in your car, you're driving. What's going to cause you to keep on moving towards the center, and what you have to fight afterwards by moving your steering wheel is the centripetal acceleration. Questions about centripetal acceleration and uniform circular motion, because I think this is the last one. And I know we've talked a lot about it. Okay, so now let's talk about some people. The velocity of an object remains constant unless an unbalanced force acts on the object. Is this Galileo's idea? Is it Aristotle's view? Newton's second law or Newton's first law? Great. So yeah. The first law is that the velocity will remain constant unless you have unbalanced forces acting on it. The second one is what law? What is the second law of Newton? Great, so F equals ma. That is just telling you that if there are not balanced forces, if the object is experiencing unbalanced forces, then you're going to have some type of acceleration. And then the last one is what? Great, equal but opposite reaction. So whatever you get to the left, you're going to get it to the right. And that, if you have your scientists thing, your page, you can write that the theories are, where's my marker? Yeah. So we have, for Sir Isaac Newton, we have the Newton's laws, and then for the first one, constant, how do we write it? We have constant V. For second, we have F equals ma, and then third is equal. I should have given you more space. I figured that afterwards. But anyway, just write it as however you can. Okay, so now we're talking about springs. This one? Sure. So, okay, wait. Okay. Now we're talking about the spring. So, if it takes a spring 2 seconds to go from equilibrium to maximum extension, what is the frequency? So, this has several parts to it. So, let's break it down. First, we have to figure out what frequency is, and we also need to know what period is. So, does anyone know the definition for period? Yes. Okay, so that's a formula. When you're talking about period, that's great though. We'll write it. When we're talking about period, we're talking about the time that it takes to complete one full cycle. So period, time that it takes to complete a cycle. In a spring, a cycle is 4 journeys from and to equilibrium. So you start at equilibrium, then you go to max extension. That's your first journey. That's going to take you a certain amount of time. Then going from max extension to equilibrium is going to take you a certain amount of time. Then it's going to take you another amount of time to go from equilibrium to max compression. You have 3 journeys, and then from max compression back to equilibrium, and you have your 4 journeys. So 1 period is 1 full cycle, which means doing those 4, moving back and forth from equilibrium. So once we have that, we can so now we're going to calculate the period. So period, does anyone know the letter we use for period? T, yeah. So it's not P, I don't know why, but it's T. So this is telling you that it takes 2 seconds to go from equilibrium to maximum extension. So this is equilibrium, this is max extension, and this is max compression. So what this is telling you is it takes 2 seconds to go here, then it has to take 2 seconds to go back, then it takes 2 more seconds to go to compression, and then it takes 2 more seconds to go back. So how many seconds does it take? 8, great. So that's your period, 8 seconds. Now, we are looking for frequency, not period. So, how can we calculate that? What is that formula we use here? Oh, I can take this away. What? Great. So, the frequency is F equals 1 over T. And it's measured in hertz, or seconds to the negative 1. And T is the same as period. Now, sometimes I'll give you the period, and you have to find the frequency. Sometimes I'll give you the frequency, and you have to find the period. If you always get them confused, how to solve them, it's pretty easy. For period, is T equals 1 over F. So it's always going to be the inverse. 1 over whatever it is that you have to find the other one. Yeah, that's a 1. That's an attempt of a 1, yeah. 1 over T and 1 over F. Okay, we're good in time. Okay, so then frequency would be 1 over T, which is 1 over 8. That is what? So yeah, it is 0.125. And the units are wrong. It's seconds to the negative 1. That's my mistake. So that is your answer. Questions about that one? Okay, so now we go back. I believe we've been going back and forth, but we go back to which is, of the following specific heats, which one is the hardest to heat? Is it 1 or 0.1? 1. So this goes back to the definition of specific heat. So basically what specific heat means, and you have it with the units, that's why you have calories over gram Kelvin. What 1 is telling you, that 1 calorie, is that you need 1 calorie to heat 1 gram by 1 Kelvin. So for water, to heat 1 gram of water from 273 to 274, you need 1 calorie. So that's what specific heat actually means. And sometimes what you've probably seen on tests with Dr. B is that he'll give you what specific heat is, and then he'll ask you more questions about it, and you have to actually understand, not only know the number, but understand what that means. Great. So basically, specific heat means that that number is the amount of calories you need to heat that substance by 1 gram of that substance by 1 Kelvin. So to increase the temperature by 1 Kelvin of 1 gram of that substance. Okay, so now let's go to the next one. The mechanical energy of an object is A, the capacity to do work, B, the same as kinetic energy, C, the same as gravitational potential energy, or none of the above. What? What? Yeah. So yeah, it is the capacity to do work. Again, if you go back to the review that I posted for exam 2, which I know we didn't do a review, but there's a review guide posted. those were a lot of the questions that I asked in that one to define different terms, because just like I told you, sometimes we don't really understand what something is. We just know how to calculate it. And with Dr. B's exams, you really need to understand everything that goes into it. So basically, mechanical energy is both, we already know it, is both the gravitational potential energy and the kinetic energy. So the potential you have to do something, and the energy that you have because you're moving. So it's the capacity to do work when you combine them. Now, the next one, if you've been going to a SI, you should do this one pretty quickly because we've done it a million times. You guys have done it like a million times. So this goes back to the graph that we did, the table that had kinetic energy, potential energy, mechanical energy, and then you had the Y. So here, if you fully understand that table, you don't have to calculate anything. So if an object has a GPE of 30 joules at Y equals 6, which is the highest position, what is the KE at Y equals 3? Does anyone know? Great, yeah, it's B, it's 15. So here's the thing. We're gonna briefly go over the table. When you have the table, you're gonna have, I don't know if that's gonna be in the test, but we covered that in class. So here they are telling you that the highest position is 6 meters. So that's what they are giving you. And then the lowest one is 0, and then this is 3. Now, at 6 meters, you have 30 joules of GPE. How much kinetic energy do you have here? Great. You're not moving. When you have the full potential energy, you don't have any kinetic energy. So what's your total mechanical energy? Great, 30. What else can we fill in the table? Great. So we know it's 30 all the way down. What about down here? When you have Y equals 0, what's going to be your GPE? If you think about the formula, your formula for GPE is what? Who knows the formula for GPE? Yeah. So negative mgy or delta y. So if you were to add y here, you can see it. So if you were to add, to calculate the GPE here and you add y here, you will just get 0. So whenever you're at the bottom, it's the energy of position. So you're at the bottom, you have nothing. What about KE? 30. Because remember, energy is the same as GPE. The total mechanical energy is the same as GPE plus KE. And where do I have that? Okay, so the formulas, I'm going to write it pretty quickly here. We have GPE equals negative mgy. Mechanical energy is E equals KE plus GPE. And then kinetic energy is the same as 1/2 what? Thank you. So yeah, mv squared. So kinetic energy is the same as 1/2 mv squared. And then GPE is the same as negative mg. And then total mechanical energy is KE plus GPE. Wait, I have them right here. Now, at the rate that they go down, So as one goes down, the other one goes up, and they go at the same rate. So halfway through, when you're at the middle of the path, you have the same for both. And because we know that the total is 30, and we have to have the same for both, it has to be 15. Every time you're at the top of the path, you don't have any kinetic energy, and you have everything GPE. As you go down, when you're halfway through, you have the same amount for kinetic energy and GPE. And when you get to the bottom, you have 30 of, you have all the energy in kinetic energy, and you have 0 GPE. Anyone confused? Now it's the time. Okay. We good to continue? Yeah? Okay. Now this is one that we went over briefly, but moment of inertia. So what is the moment of inertia of a spinning system that has 3 weights of mass equals 20 grams each at 10 meters of distance from the spin aces? So I'm going to draw it out, and then we're going to go back to the formula. So for 29, this is what you've got. You have 3 objects. We know that they spin with a mass of 20 kilograms and at a distance of 10 meters. So you've got this. This is what it would look like pretty much. Each of them of 20 kilograms, and you have a distance of 10 meters here. Now, who knows the formula for the moment of inertia? What? Wait, what? Was someone talking? And what do you have before that? Sigma. Yeah. Awesome. So yeah, you have I. Where is it? Oh yeah, right here. So the back moment of inertia. Okay, right there. It's I equals sigma, which is kind of like a weird flipped E, mr squared. R is radius, and m is mass, and this is sigma. And then your unit is kilograms meters squared. So we're going to go back to that formula. So kilograms, you have it right on the question too. Kilograms meters squared. So the sigma just means that you're going to add it as many times as you have it. So in this case, how many times should we add? Great, 3, because we have 3 objects. So because you have 3 objects, you're going to do I equals mr squared plus mr squared plus mr squared. Now, you can just multiply by 3 because it's going to be the same thing. But sigma means that if you have 3 objects, you add it 3 times. If you have 4 objects, you add it 4 times. If you only have 2, then you just add it 2 times. That would be, you know, the mass is 20, and the radius is just the distance from the object to the spin aces. So in this case, it's 10. Just make sure that you square it. And then again, mass times 10 squared plus. So what's the answer? Wait. 20 times 100, 20 times. So So we have 6. 1, 2, 3. 6,000, right? Questions about that one? What's important to know for this type of problems is when you're talking about moment of inertia, you're talking about something spinning. What? This one? Sometimes it's helpful. I would recommend for these problems, when we were doing one in SI, the distance given was actually between the two objects. So if you think about it, if you were lifting weights and you tried to rotate, I don't know why you would do, anyway, if you tried to rotate the weights, they might give you the distance from one weight to the other, but that's not the distance that you need. You need the distance from the spin aces, so in that case that would be the middle point, to the weight. So that would be your radius. We good to continue? Okay, so when does the spring have the most force? Is it at equilibrium? Is it all the way through on when you have max extension or max compression? So if you think about the equation that we use for this, is F equals kx, negative kx? Yeah, negative kx. And then, so the most restoring force you're going to have, so it's going to be at maximum extension and compression, because you're going to have the biggest displacement. That number is going to be bigger, so the object's tendency to go back is going to be stronger the further you pull it, because it's a restoring force. It's going to try to restore itself the more you pull it. So in the last class, we were talking a lot about this. And we talked about the theory of hydrogen, and we had those orbits. So basically, that's talking about the quantum theory of hydrogen. What is true in the quantum theory of hydrogen? First, only a few orbital levels are allowed. B, electron only leaves at certain specific altitudes and no others. C, each altitude has a set EPE, which is electrostatic potential energy. Or D, as electrons drop lower EPE, it emits a photon with missing energy. Or DE, all of the above. I'm going to help you out. All of the above. So basically, I know it was kind of confusing to first look at the theory. So basically what it's telling you is you have, this is your orbit. This is n equals 1. This is n equals 2. So you have an electron that lives in this altitude, or that end. When you, each one has a specific or a set electrostatic potential energy, and what happens is that sometimes they jump from, say, 2 to 1 or 3 to 2. That jump of the electron is what causes those photons of light that we've talked about. So it emits a photon of light, which is what we were looking at when we did the observation with the lamps. And those jumps are very specific for what element you're talking about. And the person that came up with this theory, if we go back to our scientists was Niels Bohr. So Niels Bohr came up with the quantum theory. So the information all about it is in question 31. Now, does anyone remember the equation with the n's that we used? The 1 over, I think it was wavelength. The Balmer formula. We used it in SI with the n's. What? Wait. 1 over wavelength equals what? Wait. 1, no, you had, does everyone have it? Okay, I'm going to rewrite it. I'm going to write it down here because I made a mistake, but. So 1 over wavelength is the same as R, which is a constant. Is that, I don't know how to pronounce his name, Rydberg constant. And then you have 1 over 2 squared, which is 4. I don't know why it's 2 squared. Negative 1 over n squared. And then R is 1.097 times 10 to the 7. So that's the constant for Rydberg's constant. The problems that I've seen with this equation, basically they ask you for the wavelength and they give you the n. So they'll give you at this level, level 2, what is the wavelength for that light or for whatever. So then you'll have to plug in that number here, do this equation, multiply it, and then inverse it because you have the wavelength down here. So let's keep going. In a parabolic arc, before a football starts to fall down, what is happening with the energy? Which one is increasing? Which one is decreasing? Or are they staying the same? Or there's nothing of those? So think as you're going up. Are you gaining velocity or losing it? You're losing it. Because at some point, you're going to stop and you're going to start going down. So if you're losing velocity, what's going down? Kinetic energy or GPE? Great. You think of the formula, 2 parts. Kinetic energy is the energy of motion. And then if you look at the formula, you have V. So your kinetic energy is going to decrease. And we know that they have to balance each other to maintain the same energy throughout. So your GPE is going to increase. Because, wait, you're falling down. My bad. You're falling down. So that's what happens before that. So your kinetic energy is decreasing as you go up. After you pass that, you're starting to go down. So gravity is acting on that football. So your velocity is increasing. Therefore, your kinetic energy is increasing. And then, because you're going down, again, GPE equals negative mgy. That y goes from, let's say, 10 to 7. So your GPE is decreasing. Did you guys understand that? I think I talked too much. We good? Yes. Thank you. So now I've told you all about it, and I circled the wrong answer. Thank you for that correction. Before it starts to fall down. That's why you read the whole question and not just look at the answers like I did when you're taking the test, because that would be sad. So it's not D. What? What did he say? Anyone have any questions? Okay. So what does torque depend on? This is another concept that we talked a little bit about in the past. Does it depend on the position on which the force is applied? How much force is applied? When is the force applied? Or for how long the force is applied? Or a combination of those? You can't see it. Okay. So torque depends on what? Position of the force applied, how much is applied, when is applied, or for how long, or a combination of those. What? You have one of them right, so which is how much force is applied. But also it depends on the position in which the force is applied. So we're talking about something, for example, spinning. If you try to make an object spin, like let's say this marker, you can't make the force, like you can't push, if you push it like this, it's not going to spin, but if you push it like this, it's going to start spinning. So it's how you apply the force. And if you remember the ice skater, when you open your arms, you start going slower, versus when you pull them in, it goes faster. So it's how much you extend the force to. And let's finish this quickly so you can ask questions. True or false? Electrons attract electrons and protons attract protons. Great. So we know positives same. If they are the same, they repel. If they are different, they attract. And this is one that you guys all asked for. The right-hand rule tells you the direction of A, angular velocity, B, angular momentum, C, torque, or all of the above. So for my reviews, every time I put all of the above, it's because it's all of the above. So that's not what he does though. But it is all of the above. So the way the right-hand rule works is if you have, where's my mark? Oh, here. Okay, so let's say you have a clock. The hands of the clock are going to move obviously clockwise. So they're moving that way. So if you grab your right hand, not your left, that's why it's the right hand, you have to move your hand in the direction of the motion. So in this case, it would be kind of like wrapping around it. And whatever your finger is pointing to, that's going to be the direction of the angular velocity, the momentum, and the torque. So in this case, it will be towards the paper. You can't see it. But if you draw it and you try to use your hand, you'll see that you can't wrap it like this because it's going against the arrow. You have to wrap it this way. So your thumb is at the bottom, so it's pointing towards the paper. It's the same thing with the Orlando eye. It moves, I don't know, depending on how you see it, it moves one way. So it's the same thing. You can either, and it's kind of like your hand has to hurt to do it or has to bother you, but that's when you know it's going towards like the paper. And then if it's going clockwise, it's going to go towards you. So it's just to tell you the direction of the angular velocity, angular momentum, and torque. Now, where does a comet in an orbit move faster? Is it at perihelion, aphelion, or the velocity stays the same? So perihelion is the closest point in an orbit. So for Earth, it would be the closest point to the Earth, to the sun in the orbit. So if we have the sun, you guys get it? And then you have Earth right here. So let's say this is your orbit. This would be, let's just pretend this is closer. This point, which is the closest point from the sun, that would be perihelion. And then the farthest point will be aphelion. So it moves faster at perihelion, and I'm going to tell you why. Sorry, wait. You got a question? That's clockwise, yeah. So when you're at perihelion, you have to move faster because you have to maintain, you have to conserve your momentum. Your momentum stays the same throughout. And if we go to the L equals mRV, which is the orbital angular momentum formula, you have to think in terms of your radius, because the L has to stay the same, your momentum has to stay the same as you as your radius increases to stay the same, your velocity is reduced. So the further away you are from the sun, the bigger your radius would be, meaning that your velocity has to decrease to stay the same. It's kind of like the same with GP and kinetic energy. When as one goes up, the other one goes down. Same thing with radius and velocity when you're in an orbit. So when you're in perihelion, your radius is the smallest, so your velocity is going to be the biggest. So you're going to be moving at a faster rate. Questions about that? Again, I know I've said it a few times, but when you're taking tests with Dr. B, a lot of the questions are formulas that are applied. So as long as you know what formulas apply to what examples, you can use that understanding to solve instead of just memorizing a fact like at perihelion, it moves faster. And then I think 2 more questions and that's it. Oh, and then we have the matching one. Okay. If an object has been in free fall and dropped a total of 52 meters, how long has it been in free fall? So we're talking about free fall and we're talking about drop. What formula do we use? Drop distance. So we already said that the drop distance one was d equals 1/2 gt squared. So for the purpose of having enough time, I'm going to go over it pretty quickly. So you will have to solve for t, and that would look like t is the same as the square root because it has that 2 there. So this one has to go multiplying, so 2d over g. And if you do that, I don't have the number, you would get 2 times the distance, which is 52. 52 times 2 divided by gravity, which is 9.8. And the square root of that is, does anyone calculate it? $3.25. Great. 3.26 seconds. So again, it's a matter of being able to use a formula that's not for time, but that has time to apply it. And every time you talk about drop, this is what you're looking at. And I don't want to forget about it. But the impulse equation, every time you hear the word it stopped or slowing down, the formula you're usually, like 95% of the time you're going to use is the impulse formula. Does anyone know it? Yeah. So the impulse equation is F delta T equals M delta V. And if they ask for the impulse, what you have to do is multiply the force by the time. Questions? Again, impulse equation, every time you talk about stopping or slowing down, that's the formula you're looking for. And what is the net force direction of the rightmost electron? So is that moving to the right or to the left? Great, to the right. So it's moving to the right because this one is attracting it and this one is repelling it. When you talk about, when we're looking at electrons and protons, you are only focusing on one. So you have to think about all the other ones stay where they are at, and I'm only moving the one that they are telling me. So is that one going to move to the right or to the left? That's what you're looking for. And then pretty quickly, what is the overall modulation of sound from mixing two different frequencies? Great. Beat rotates about a fixed point. Rotational motion. Peaks align with troughs. Constructive or destructive? Destructive. B. Peaks align with peaks. We have constructive from point A to point B on a straight line and no spinning. It's translational and then has both of them. You have two, so it's a combination of both of them. Now, okay, so before you guys go, pretty quickly, make sure that you give back all the evaluation, the study union evaluations. And I know we didn't get to cover all the scientists. However, you guys, I'm just finishing. I know we didn't get to cover all the people here. However, just go over them. Some of these are pretty straightforward, like Edmund Halley, he discovered the comet. So we talked about him with orbits. De Broglie, we just talked about him. So when we talk about electrons and, yeah, when we talk about that, Niels Bohr, the quantum theory of energy, of hydrogen, Balmer's theory, I will go over Max Planck. I would really go over him because Dr. B talks a lot about him, Galileo, and Coulomb. Wait, before you go, please, if you have a test tomorrow, be there at 10, not 10:30, and sleep. Don't be sleep deprived, and like caffeine hasn't kicked in, and then you just fail because of that. Sleep, and thank you guys for a great semester, and good luck on your finals.